All right. Yes, sir.
5.4, number 33.
5.4, number 33. Stalling technique 1 is to repeat what the person has just said and then to explain what you just did. And then you just give up and...
Technique 3 is to explain.
Yeah. The left side or the right side. I don't get those stupid commercials. The left side's dumb. The right side's dumb. All right. So 5.4, number 33. Okay, so this is where we finally get into using f of b minus f of a officially, right, for the integral of something. Wow. 33. Okay. Is that the x over 2 minus 2 over x thing?
Yeah.
All right. 2. Yep. X over 2 minus 2 over x. Okay. So the section 4 that somebody brought up a minute ago, that's a part of this whole thing. It's just being able to find the antiderivative by itself. Now we've gone through the whole thing about what does it actually represent. So we know that it represents the area underneath the curve that it came from. So what now we know the question this thing is asking is, what's the area under this function, between this function and the x-axis, from 1 to 2? Cool. And we're cool with negative areas. So it's very possible this could come out to be 0. Maybe it's got the same amount on the top and bottom. Could come out negative. No worries. So now it just boils down to, can you take the antiderivative? Can you think backwards? Can you tell me what that would have come from?
X squared.
Yeah, so it would have had, you could look at it as 1/2 x. So when you take the integral of that, it's going to be x squared over 2, and there's already over 2 there. So it'll be x squared over 4. So far, so good? So I always think about it like, if I said to rewrite this in logarithmic form, I love doing this to people. You're like, what the hell's it got to do with it? But you got to kind of think, okay, 7 and the power. And then to check yourself, you go, okay, 7 to the x equals m, bam. Because that's the easier way to go, right? How do you check yourself here? Take the derivative, 2 comes down, cancel the 4, bam, okay, that looks good, right? The check is quicker than the original thing was, so you might as well take a second to check it. Over here, this may be a little easier, because there's only one thing that could be. Yeah, it's got to be 2 ln x, and I really don't need the absolute values just because I know the area I'm in is on the positive side of the y-axis, so I'm good. Positive x's. And then I go from 1 to 2, and I just plug and chug.
And that's big f of x, right?
Yeah, this function here is big f of x. If you want to look at this as little f of x. But again, that's just a choice of symbol for what you just did. It's unnecessary to really think about it that way, but that's the connection between this and the fundamental theorem of calculus, the way they write it. Yeah. So when you plug a 2 in, that's like f of b. And big ass f of b and big ass f of a. I like it. So, was the trouble in the
ln x thing.
Oh, okay. Yeah. Absolute value wouldn't hurt you here, but it's not necessary. And you just plug stuff in and see what it comes out to be. Normally on a test, it's always good. So, for example, here, this will be 1 minus 2 ln 2 minus 1/4 minus, what's ln 1? 0, good. So it's better, when in doubt, leave it as the exact answer. Unless I say round your answers to the nearest whatever, then you might as well take it to a decimal, right? Or if this has some physical meaning, you might want to take it to a decimal. Like maybe this represents the amount of money my company brought in. So you want to take it to the decimal and write it as a money amount. Okay. Anything else from homework? Yes.
It's going to sound kind of dumb, but at the beginning of 5.4, everything else is fine, but 3 and 4, I don't know why, but I can't, like, it's like so difficult for me to I don't know, match up the two equations. I feel like that was the hardest part.
I got you.
Like, maybe let's just do 4.
4. 4 looks like it's the other one. 3 might just be, 3 is going to be just, what do you call it? Trig identities. I think it's going to get you through that. All right, so you got to look up your trig identities. Because to check this integration, you take the answer from the integral and you do like we just did, differentiate it. So 3 is going to involve some trig identities. So that shouldn't be as big a deal. Just got to look those up. 4 looks kind of freaky. All right. And it's not okay just to say, well, this is obvious, and then move on. Oh, yeah, come on. That's like asking me to prove 1 + 1 is 2, Jeff. Come on. I want to point out something. I don't know if you guys have looked. One thing you should always do when you get a new book, especially in math, is to see what's in the front. Not much, some advertisements. And what's in the back. For example, there's a whole table of integrals in the back. Good thing to know. So this is actually probably one of these in there somewhere. I'm not going to waste time. But in the very back, there's several reference pages. And the last few pages of the reference pages are integrals. There are trig identities in there also. Very good stuff to know. But you always look in the front and the back of the math book when you get a new math book, because there's going to be some kind of cool stuff there if it's a good book. So now you just got to take the derivative of this. What's the only variable, of course? X. So just keep that in mind. The C I pretty much can just forget about. So to check this, you can take this guy's derivative, but let me rewrite this a little bit. And then it's just really, what's the rule that I have to apply? Product rule. Exactly. Cool. Right, so you got to do, this is just a constant. It's going to come for the ride. Derivative of this, leave that alone. Derivative of that, leave this alone. Right? So this comes for the ride. Derivative of this one is going to be what?
Just X.
B. Gotcha. And then leave this guy alone. Plus, derivative of this is going to involve a 1/2. It's going to kill that 2. So there's a 1/2 that came out. A plus bx to the... Yeah, what really sucks is when you're in the integration and all of a sudden you have to take a derivative. So you got to turn that, you got to crank that gear, right? Go in reverse, going forward, whatever the hell you want to call it. So this would be negative 1/2. And what's the derivative inside here?
B.
B again. And now you just have to try to make that look like this. No big problem. And the nice thing to notice is the fact that this already has that underneath, doesn't it? So it's telling you how to do this. And when you have the form of the answer, you force that thing to look like that. So he's already got it underneath. You're going to give it to him. What happens here real quick? Yeah, so I get 2a plus bx to the 1/2 over 3b plus, let's see what all happens here. I get over a plus bx 1/2, 3b, one of the b's cancels, bx minus 2a
Where'd the 1 over 3b squared come
And
from?
it comes along to the right both times, right?
Yeah, this is constants come for the ride.
Now
The
go
2 died because the 1/2 came down.
That's what I was.
Cool. I just didn't want to write the line same over and over. Whew. So now, if you, how do I make the LCD? Multiply this by the same thing. So it's going to be twice a full one of these plus bx minus 2a over 3b times a plus bx to the 1/2. So somehow that 3b is supposed to go away.
Simplify the top.
Yeah, 2a, let's see what we get. 2a's go away. You get 2. You get, oh, good, 3bx. Awesome, Joe. Just have faith, Joe. A plus bx to the 1/2. 3b's go away, and that's that. Sweet. I just broke my own rule, which is never stop and say, that can never become that. Just do the next step, and you'll see something you didn't see. All right, but at this point, if I ask you to differentiate something, I almost don't care what it is. You should go, oh yeah, no problem, sweet, give me more of that, right? Because at this point, differentiation should be, it's the one that you can sink your teeth into. It's got all these rules, and it's got all these things that we know, and integration is the one we don't know much about yet. We know very little about it. In fact, the whole next semester of calculus would be devoted to learning everything else, or not everything else, but a lot more about integration. Okay, any other questions from homework? What's up?
Those seem to be confusing. The last few in 3.4, like, I don't know, 4.
We're at 5-4?
Yeah. 54, 5, 4.
Okay. The last few in 5-4, like which problem, sir?
Let's see. Let's just do 50. I was. That's okay.
Oh yeah, good. All right, I like this. This actually leads into the next section we're going to do. So number 50 gives you this thing. So, X and Y axes, completely arbitrary. Agree or not? You should agree because it's true. Right? I mean, if I have a shape sitting in space, we can consider the fact that we come in with the coordinate system, we place it on top. And normally we put the origin at a good point. Right? So here's an example of a coordinate system that exists and somebody put a function on top of it, the crazy person. But if it was turned this way, or, inverted so that this was actually here, it would look a lot better. If it looked like this, that looks a little more like something I'm used to. Find the integral, find the area under there, right? So really, instead of doing that, we work with the way it is. We just don't integrate with respect to x. We integrate with respect to y. Because if I look at it this way, I got all my little rectangles looking like here, blah, blah, blah. So as y changes, I can move along through that area. So let's start this process and let's see what happens. So if I want to integrate with respect to y, what are my limits?
0 to 1.
Yeah, y goes from 0 to 1. Now what's the function that I'm actually integrating? Here's where you got to be careful. If it's integral dx, this function has to be a function of x. So if it's integral dy, now I got to be careful. This is not in general, because when you do stuff like, this is true, like double or triple integration, you can kind of do this in steps, and sometimes it's function of x and y and z and all this kind of crap. But for us right now, for us to be able to do it with what we know, if it's dx, that's got to be a function of x. dy, this better be a function of y. Because what I really want to do, remember what's going on, as I change y, as I move along the y-axis, So I'm not going to have a bunch of little yi's instead of xi's. So what's my height going to be set by? For a specific y, it's going to be the output for that y. So I better have a function of y. So right now I have a function of x. And it's pretty damn easy to turn that around. X is a function of y, would be y to the fourth. Give that guy a lot of room. Because, I mean, if you just twist this thing around, of course it kind of does this, because this is the positive y. So I'd have to kind of flip it like that. This would be just that parabola. That would just be the part of the parabola. You know, you got to do it like this, plus look at it reversed. You guys semi with me? This idea of integrating with the x or y has become an issue with choosing the right one at the right time. Sometimes you can do it either way. And one way is crazy hard, and the other way is stupid easy. So it's good to know I can do it either way. So then how do I, and then now this is not too bad. What's the integral of y to the fourth? 1/5 y to the fifth from 0 to 1. At 0, it's 0, so the only thing is at 1. 1/5. If I did this, if I integrated from 0 to 1 of the original function, I would get this area, right? You with me? And now I'm curious. So this would be x to the 1/4. Let me just show you something real quick. You guys semi-cool with that? Semi, okay. What's the integral of this guy? Be careful. X to the 5/4, so you better put the reciprocal out there from 0 to 1, so that would be 4/5. Now what's this box? What's the area of the box? 1. What's 1 minus 4/5? 1/5. All right, sweet. See, there's a... Right? That's the cookie cutter approach, right? Find the area that you don't want to include, and you just cut it from the dough. That's a whole other... If this thing is just disgusting, but the other side is really nice, then just look at the whole thing as the dough, and then just cut the piece you don't want out. Right? Doesn't necessarily happen a lot, but it's there if you want. Okay. Anything else from homework? I mean, the thing about math is just knowing, one big part of it is just knowing what you're able and allowed to do, right? Just being aware that that is okay to do something like that. All right. So I'm going to do something that I really should have probably been doing the whole time, but oh well. I'll learn. And that is using the e-textbook to show some illustrations. Normally I used to not even use it because we didn't really have it. And then I started using it for Calc 3, where you have three-dimensional objects that you want to rotate. And I'm like, I can't draw in 2D. My stick figures doesn't even look right, so I needed help. Log in here and turn this guy up.
So like before all this crazy technology, would teachers just not be able to show examples?
They had to learn how to draw 3D really well. So I almost want to believe that there used to be a 3D drawing class for math teachers. There had to be. Now it's not so required. I'm really kicking myself because I forgot something in my office that was low tech but was really cool. Shit, what is it? Yeah. Alright.
Take 120? Or to not take 120? Yeah, I didn't try and test it out. took it. I took 120 yet. I haven't taken 141 though. Or 140.
All right. So what we're getting into tonight is how to find volumes. We've been talking about how to find areas. But now we're going to step into big pile of volume, right? And the cool thing, I mean, one thing I want to go into this really making sure you understand. Calc 3 is where you're really dealing with all three dimensions. I'm going to try to show you, because one thing you get worried about as a student is, do I have to actually draw these 3D pictures? Because Jeff just said he can't do it, and what the hell? Well, if you're an artist, feel free. I am obviously not. But I want to make you guys realize that everything we're doing is still just dependent on a single variable. When you get to Calc 3 and you're really doing true three-dimensional calculus and you're having to deal with integrals that would look like integral dx, dy, dz. Yes. Right? That's where you're truly going through the whole volume. Here, there's situations where I don't have to do all that. I can simplify it a lot. So the general idea is if I have a 3D shape, so I got a 3D shape sitting up here. Obviously, it's 3D, so there really should be a third axis coming off or out. Normally it's drawn at a slight angle. But the fact is I don't need it. Because at x, that by itself defines this cross section.